This is the orbit of the moon around the Earth. Clearly the distances and sizes are not to scale, but I want to use this to illustrate the different types of lunar months and what they have to do with solar eclipses. The moon orbits the Earth once every 27.3 days. You can see here that the moon starts in between the Earth and the Sun and returns to that point exactly 27.3 days later. This is called a sidereal month and describes the time it takes for the moon to return to the same position in its orbit relative to the fixed background of stars. So why don't we see eclipses every 27 days? Well, the Earth is also orbiting the Sun. This orbit takes 365.25 days. So after every sidereal month, the moon has to travel a bit farther to reach the same position in between the Earth and the Sun. To be precise, it takes 2.2 extra days, meaning it takes the moon 29.5 days to return to the same position in relation to the Earth and the Sun. We call this a synodic month. This is the most useful lunar month, as it tells us how often the phases of the moon repeat. So why isn't there a solar eclipse every new moon? It's because the orbit of the moon around the Earth is at a slight angle in relation to the Earth's orbit around the Sun. The real inclination is only about 5 degrees, but I'm exaggerating the effect for this animation. The result of this angle is that for most new moons, the moon is either too high or too low to cause an eclipse. The 2 points on the moon's orbit where it intersects the Earth's orbital plane are called nodes. The blue node is the ascending node, where the moon travels upwards, and the red node is the descending node, where the moon travels downwards. If we look at these nodes from the side, you can indeed see that at these points, the moon is vertically aligned between the Earth and Sun. The time that it takes the moon to orbit and return to the same node it started at is 27.2 days. This is known as a draconic month. Now the alignment of these two nodes between the Earth and the Sun leads to approximately 2 eclipse seasons per year, separated by 173 days. During these 2 seasons, one of the nodes comes in close enough alignment to allow a solar eclipse to happen. Because the Earth is fairly large, the moon does not need to be exactly at the node to cause an eclipse. Even if a new moon is slightly offset from the orbital nodes, it will still cast a shadow on either the top or the bottom of the Earth. This means that each eclipse season lasts for about 35 days, during which a new moon will lead to at least a partial solar eclipse. Since new moons occur once every synodic month, or 29.5 days, each eclipse season is guaranteed to have at least 1 solar eclipse, with some seasons having 2 solar eclipses. If we look at the past several eclipses, we can indeed see 1 eclipse roughly every 6 months. If we look forward to 2029, we see 2 eclipses separated by only 1 month. This is because 2 new moons occurred in the same 35-day eclipse season. The first casts a shadow on the top of the Earth, and the second casts a shadow on the bottom of the Earth. Now, even when the moon perfectly lines up between the Sun and the Earth, it does not always cause a total solar eclipse. The moon's orbit is slightly eccentric, meaning it's not a perfect circle. I'm exaggerating this effect for the animation. At its closest, the moon is about 360,000 kilometers from Earth, and at its farthest, it's about 405,000 kilometers from Earth. As a result, when an eclipse occurs while the moon is too far away from Earth, it does not completely eclipse the Sun when viewed from the surface. This is called an annular eclipse. The point in the moon's orbit that is closest to the Earth is called the perigee. Total eclipses can only occur near the perigee. The time that it takes the moon to orbit and return to perigee is 27.6 days. This is known as an anomalistic month. It might seem odd that the draconic month, anomalistic month, and sidereal month are all different lengths, even though they all describe the time it takes for the moon to reach the same spot in its orbit again. This is where long-term changes in the moon's orbit come in. There are 2 main types of precession that change the moon's orbit over time. First is apsidal precession. The moon's perigee rotates eastward around the Earth once every 8.85 years. This leads to the anomalistic month being slightly longer than the sidereal month because it has to catch up to the preceding perigee. Second, there is nodal precession. The moon's ascending and descending nodes are rotating westward around the Earth once every 18.6 years. This leads to the draconic month being slightly shorter than the sidereal month because the nodes shift slightly. These long-term trends in the moon's orbit are minor, but they are important to consider when trying to predict future solar eclipses. All of these factors must align for a total solar eclipse to happen, which is why they are so rare. However, when we do see a solar eclipse, we can predict when a similar eclipse will happen again. A new moon occurs each synodic month, but since the other lunar months are different lengths, they fall out of alignment. In this table, you can see that after 1 synodic month, 1.08 draconic months have passed, meaning the moon has passed its orbital node and eclipse cannot happen again. As more synodic months pass, the 3 months get more and more out of alignment. After 223 synodic months, or about 18 years, we find that the months line up once again. 223 synodic months is 238.992 anomalistic months and 241.99 draconic months. This means that all the relevant factors in the moon's orbit have returned to the same position and another solar eclipse will happen again. This period of 223 synodic months is called a Saros, and the series of solar eclipses that has produced each Saros is called a Saros Series. From this animation, you can see two solar eclipses, one Saros apart. The conditions that created the solar eclipse in year 0 are almost identical to the conditions in year 18 due to the alignment of the lunar months. The rotation of the moon's orbit, even though it looks different here, is the same in relation to the sun because one Saros is slightly more than 18 years, and the Earth is at a slightly different point of its orbit. Let's use the August 21st, 2017 total solar eclipse as an example. This eclipse was a part of Saros Series 145. The next solar eclipse in this series is on September 2nd, 2035, but it will mostly occur over the Pacific Ocean. Because one Saros is not an integer multiple of the number of days, each subsequent eclipse in this Saros series happens about 8 hours offset from the previous eclipse. This means that the eclipse's location on the Earth shifts westwards about 1/3 of the way around the globe each time. As a result, every third eclipse at a Saros series will take place around the same location on Earth. After that, there will be an eclipse on September 12, 2053 that travels through northeastern Africa. It will return to the Americas on September 23, 2071, but it will be just south of the United States. But these series don't last forever. Saros Series 145 started in 1639 and will continue until the year 3009. This is because the alignment between the synodic month and the draconic month is not exact, and the differences add up over time. Saros series can last between 1200 and 1600 years, and will produce 69 to 87 eclipses. Because the anomalistic month also does not line up exactly, some Saros series will change from producing total solar eclipse to annual solar eclipses, and vice versa. Saros series do overlap. There are about 40 Saros series happening at any given point in time, each producing eclipses every 18 years. Right now, there are 12 Saros series producing total solar eclipses, 13 producing annular eclipses, 1 producing hybrid eclipses, and 14 producing partial eclipses. There are many other types of eclipse periods besides the Saros, and while I won't cover them here, I encourage you to research on your own. So while eclipses do happen 2 to 3 times a year, the likelihood for a total solar eclipse to happen over one particular spot on Earth is quite rare. I hope this video helped you understand how complex and amazing solar eclipses truly are. Thanks for watching.